0 to 50 exaflops in under a year. 50 exaflops, just to spell this out, is 5 followed by 19 zeros of floating point operations per second. We deployed this amount of inference capacity for our customers in just under a year. It sounds cool, right? But the truth is that it was very painful and hard, and actually mostly not that much fun. I'm going to share with you our hard-earned lessons as we rapidly scaled the world's fastest AI inference service. But first, we'll start with some context. At Cerebras, our mission is simple: to accelerate AI. That means accelerating AI development, AI adoption, and most importantly, accelerating AI applications. We're doing this by reinventing AI compute. We invented the chip of massive scale. This is an image of a single Cerebras Wafer Scale Engine chip. That's just one chip. And that one chip packs a massive amount of compute and memory: 900,000 cores, 125 petaflops of AI compute, and 44 gigabytes of on-chip SRAM. Those numbers are actually about 50 to 60 times higher than today's most advanced GPU. And this is what's behind our ability to massively accelerate AI development and AI applications. Now, of course, a chip by itself is useless. So we package these chips each one into a single system. We interconnect this system into clusters, and then we deploy these clusters in liquid-cooled data centers. This image here is from one of our data centers in Texas. Data centers by themselves are not that useful if they're not connected to the internet. So we're connecting our data centers to the internet so that using the world's fastest inference is as simple as making a Python API call, or whatever language you prefer. Now, what does fast inference mean? It means two things: low time to first token, latency, and second thing, high token generation speed. Now, in this chart, you want to be in that green box, that light green box over there. That's where we have low latency on the y-axis and high speed on the x-axis. Now, here's some data from an independent third-party provider called Artificial Analysis. They benchmark API providers, models, and in this case, this is data for a benchmark they did for OpenAI's latest open model, GPT-OSS 120B. You can see the crowded space on the left side. Most of these inference providers are running on GPUs. And I'm not sure if you can see Cerebras on the far lower right side, far away from everyone else. I actually had to add a fat orange arrow since most people miss it since it's so far to the right. Cerebras is the world's fastest inference, and by a huge margin from anyone else. Now, this massive speed advantage is not just for OpenAI's GPT-OSS. Here's some data from a few other models, open models from Mistral to Perplexity, Qwen, Llama 4, and of course, GPT-OSS. Cerebras is about 8 to 20 times faster than GPUs serving exactly the same model. So in the years since we launched the service, we've seen tremendous traction and adoption. And we actually deployed over 50 exaflops. And we're on track to double that in the next 6 months. We scaled to multiple data centers and actually are launching a new data center in Europe pretty soon. We have about 100,000 developers on our paid and free tiers and have onboarded hundreds of enterprises. Many of our customers operate at the bleeding edge of AI, what we'd call AI natives, including AI leaders like Meta, Mistral, Hugging Face, IBM, and many, many others. And we're just getting started. All right, now that we have context, and hopefully you're excited about fast inference, let's go back to these painful lessons we've had of scaling to a massive scale in such a short amount of time. Take a look at the diagram here. This is a basic system architecture for a typical inference service. Start with a CDN, then we have a control plane with an API exposed, some databases on the back end, and from there, data plane with the server, the inference server, storage for model parameters, and of course, our clusters of accelerators. Pretty standard. Now let me ask you a simple question. Which component or components in this diagram are likely to fail? Take a moment to think about that. Exactly, all of them. The sad yet sure answer is that each and every component in this diagram will fail at some point, guaranteed. This is our first and arguably most important lesson. If something can fail, it will fail. It's actually something called Murphy's Law. And my own personal addition to that law is that that failure will happen at the worst possible time. Now, these are some of the failure modes in which these components may fail. Your cloud region will go down. It's actually happening not super frequently, but does happen at least once a year. Your CDN will go down with it. Your software, your own software, is going to fail in ways you never imagined. Every hardware device you rely on is going to fail at some point. And even worse so, from our experience, even your own health poles are going to go down. How to prevent these? Here's some of the effective ways we learned to prevent these. You want to first identify single points of failure in your system, both in software and in hardware. And then you've got to introduce redundancy so that when the failure happens, and it will happen, your redundancy saves you. You want to implement monitors throughout your system so that when something goes down, you know immediately, and hopefully before your customers do. And lastly, when deploying models for inference, make sure you have redundant replicas in a separate region, separate data center, because something will happen at some point that will prevent access to that replica. With redundancy, you're going to save the day. Lesson number 2, optimizing for system performance, not model performance. Now, machine learning people, like many of us here in the room, love to tinker and optimize models. It's a lot of fun. But the reality of production-grade AI systems is that these systems are compound systems, with the model being just one component out of many other components, like we've seen in the diagram before. And so your key performance metrics may not be dominated by the model performance. Often the bottlenecks are quite different. And I'm going to give you a concrete example from our own experience optimizing our services latency, also known as time to first token, or TTFT for short. We set upon trying to optimize TTFT, and no matter how much we optimize the model inference itself, that forward pass in the neural network, we could not move the needle significantly on the customer-facing end-to-end TTFT, or latency. Now, it turns out most of the latency was actually coming from outside the model. It was coming from the network latency, the API overhead. We were able to cut down our TTFT by half, just by doing some pretty basic, traditional, good software engineering. Introducing HTTP2 in our origin servers. That cut down the handshake significantly. Increasing our edge server distribution so that we're closer to our customers no matter where they are. And then lastly, reducing our API gateway request handling overhead. This traditional engineering enabled us to cut our latency by half. So remember, optimize for system performance, not the model performance. Onwards to lesson number 3, request handling pipeline. That's a critical part of any inference service, arguably any AI system. That's where you handle authentication, authorization, rate limit checks, routing to the best data center, best replica for serving the request. Sounds simple and straightforward, and that's how it actually starts. But the challenges start arising as you scale the service, as you scale the business. The simple pipeline doesn't cut it anymore. As our control plane became multi-region, we had to distribute our business logic, distribute authentication, authorization, distributed rate limits, up to distributed billing. Not trivial. As we scaled to multiple data centers, we had to invent new routing logic that will optimize request handling, balancing availability with latency. And as we launched advanced features such as prompt caching, we had to update our routing to make sure we route requests to where the request prefix was cached before, doing sticky routing. As we started onboarding more and more enterprises, these are customers of higher value, we had to introduce priority queuing. But we had to do it in a way where we don't starve the lower value customers. Sometimes we had to introduce multiple rate limits for the same account, because that's what enterprise customers need. And lastly, as we scale to millions and tens of millions of tokens per second for our models, we had to reinvent our rate limiting algorithms so that we avoid denying service from customers at spike and other challenges. So remember, your inference request pipeline is either going to evolve with your business or it's going to break, and of course, better if it evolves. Next lesson, embracing for bot attacks. Last year on June 4th, there was a single day where three of the top AI services out there were down for a few hours. I'm not sure if you all remember that. ChatGPT, Claude, Perplexity were all under bot attacks, potentially coordinated bot attacks, taking them all down for multiple hours. Now, this should not be surprising. AI compute is scarce, and it's expensive. And there are many malicious actors out there who are always trying to exploit AI services, especially when these services offer free tiers. In our experience at Cerebras, it's not a question of if you'll experience a bot attack. It's a question of when it will happen. Our service has been hit by these attacks multiple times in the past year. So what can you do about it? There are three areas to focus to build resiliency. First, prevention. Put country and IP blocks in place. Some countries and IPs are notorious for being bot attack origins. Buy and configure a WAF, Web Application Firewall, which will handle a lot of the heavy lifting for you. And introduce strong identity checks, such as payment instrument, phone numbers. Email for identity is today not sufficient. After prevention, you want to move to detection. In case prevention did not work well, you want to know when you're under bot attack and know as quickly as possible so you can do something about it. Introduce high watermark alerts, customer experience monitors, resource usage alerts, so when there's abnormal activity, you know immediately. And then once you detected, you have to move to mitigation as quickly as possible. You want to introduce on-call playbooks, feature flags, so you can turn things on or off without having to redeploy your service. Admin tooling to allow people to configure the service very quickly. And wildcard-based user block lists are super critical because often these attacks are coming from very specific domains. Our fifth lesson is about observability and the recognition that observability work is both critical, but then it's also never done. It's always work in progress. Inference, as we learned, is a critical service that has to be up 24 hours a day, 365 days a year, with no time off, because it is powering critical applications for our customers. Even more than that, it has to perform consistently well always, or else your customers will be impacted. For that to happen, you want to know when how the system is behaving and how different components within the systems are behaving. And you want to know that at least on a per-minute resolution. How do you do that? Two main tips. First, you got to think about metrics and instrumentation very early on. In fact, you've got to start designing this when you design your features. You want to define your KPIs, the KPI targets. You want to make sure you have in your infrastructure a time series database. And then you want to make sure you have self-serve dashboarding and alerting, so any team building new features can self-serve their way into emitting metrics, storing these metrics, querying them, and alerting on them. Then you want to make sure your observability is resilient for failures. You want to introduce redundancy, like we discussed earlier. You want to have global exception handlers. And because your system at some point you have to assume is going to fail, you also want to rely on external testing, synthetic tests, with monitoring and observability. So even if your infra is down, you have other infra that can allow you to know what's going on. These are a few examples from our own dashboards at Cerebras. Today we have dozens of dashboards monitoring our service with thousands of metrics. These examples here show a few of our widgets tracking token generation speed, time to first token, percentiles, generation throughput in tokens per second, as well as availability for specific models. Our last lesson for today, building a culture of operational excellence and starting to build it from very early on. On the right here, some of you may identify this arcane device. It's called a pager. And a personal story, when I joined Amazon about 10 years ago, this was the first swag I got, just like any other engineer in the company. So almost every engineer at Amazon is part of an on-call rotation and will be paged if his code breaks in production. Amazon has one of the best company cultures out there for operational excellence, and indeed their services and products are notorious for their uptime and reliability. So that's something to try and imitate to some extent. So shit will happen in production, even if your team and code and systems are best in class. You want to have a culture where you can handle breakages quickly and effectively, from detection through mitigation and up to prevention. In our experience at Cerebras, a big part of building a culture of operational excellence is about setting key expectations across the company. The first, most foundational expectation is that if a person or a team is shipping code to production, that person and team own their code in production. If you ship to production, you own your stuff in production. That's super important. And what this means, it means every team shipping to production has a 24/7 on-call rotation. It means that team that has an on-call rotation because they're shipping code to production also owns their own operational dashboard, owns their alerts. So if things break, their things break, they know immediately and can handle it. And it also means that you define incident severities across the company. And every significant severity that happened, once it's mitigated, the team who owns that incident is conducting a detailed post-mortem, identifying the root cause, the corrective actions, and the preventive actions. This is super important because this is how you get better with each and every failure. All right, we're at the end of the talk. Thank you for tuning in. I hope this was interesting, but more so, I actually hope this is going to be useful for you all as you build and scale AI services and applications. Thank you.